Welcome to all of you in the course of blockchain. So, till now we have discussed about the permission model of blockchain, and we have looked into the details of Bitcoin network as an example of permission blockchain, and we have seen different aspects of a Bitcoin network where a user can join in the network and start doing the transaction. So, in this particular class, we will discuss about one interesting property of a blockchain network or rather a set of algorithms which help in achieving consensus in a distributed or a decentralized network. So, we will look into the details different methods of consensus and how they are applicable for a general blockchain environment and with a special case of Bitcoin network. So, this concept of consensus is an interesting topic in a decentralized or in a distributed network. So, consensus means it is a procedure to reach in a common agreement in a decentralized or in a distributed platform. So, here is an example of a typical example of a consensus mechanism. You can assume that in an army there are 4 generals and the generals are taking some kind of decisions. And when the generals are taking the decisions in a decentralized on a distributed way, that means they have their own policies to take the decision. They can either make an attack or can retreat from the attack. Now, in a consensus algorithm, these generals individually they express their opinion, their individual opinion, and from their individual opinion by applying some kind of choice function which can be the majority decision in this particular case. So, by applying such kind of choice function, the environment or the system finally decides what to do next. So, here in this particular example that 3 generals they are making a choice towards attack. So, with the majority principle the system can come to a consensus that they should make a attack collectively. Now, this kind of consensus algorithm it is important for a message passing environment in a distributed system. So, let us first look into that why do we require consensus. So, in a traditional or conventional distributed system we apply consensus to ensure reliability and fault tolerance. So, by mean reliability and fault tolerance it is like that in a decentralized environment when you have multiple individual parties and they can take their own decision, then it may happen that some nodes or some parties or some individuals are working as maliciously or they are working as a faulty individual. So, in those particular cases it is important to come to a common decision or a common viewpoint. So, having a common viewpoint in an environment where people can behave maliciously or people can crash or work as a faulty way, it is a difficult thing. So, under this kind of distributed environment our objective is to ensure reliability, that means to ensure correct operations in the presence of faulty individuals. So, there are multiple examples for consensus in a distributed system. If you think of a distributed database where the transactions are going on from multiple points of sale, say from multiple ATMs, multiple banking sectors, the transactions are coming in. During that time consensus is an important aspect. So, for example, you want to transact some money from one bank branch to another bank branch, another account in another bank branch. So, during that time you need to come to a consensus that all the bank branches need to decide that well these transactions is a valid transactions, and after deciding that this transaction is a valid transaction they should commit the transaction. Then another example of consensus is state machine replication. So, the state machine replication is an important aspect of any distributed protocol. So, say for example, if you want to run some kind of distributed protocol over a network, every individual nodes runs the current protocol, current version of the protocol, and they store the state of that protocol in different state machines. So, the entire execution part of the protocol can be represented as a state machine. Now, this state machine need to be replicated into multiple nodes, so that every individual node can reach to a common point or common output of that protocol. So, the state machine replication is an example of consensus. Then another example of consensus is clock synchronization or distributed clock synchronization. Say you have multiple clocks in your network, and every individual node tries to find out that which is the most updated clock or which is the most current clock. So, they should make a consensus among themselves and come to a single clock, and by applying this kind of clock synchronous clock architecture across the network, they can do further operations. So, these are the typical examples of consensus in a traditional distributed system environment. So, let us look into that why achieving consensus can be difficult in a certain scenario or typically in a message passing system. So, here the example that we had considered earlier. So, we are considering that example again, that we have now multiple generals. Now, these generals are utilizing a message passing environment to communicate their viewpoint to others. Now, you can just think of that every individual generals, they are making a telephone call to the other general and then communicating their viewpoint to others. Now, let us look into this diagram. So, this general, it is sending its information to its neighboring generals, this one and this one. Now, whenever this general is sending the information, the general makes a telephone call to the other two generals, say G1 and G2, and inform his viewpoint that they should now attack. Similarly, this general, say the general G3, he again makes a phone call to G2 and G1 and send his decision that the soldiers should now make an attack. But this particular general, say G1, this is a malicious general, and this general make a malicious call, like he makes a call to one general, say G4, and ask for retreat, whereas whenever he is making a call to general G3, he is saying as an attack. Now, in a complete distributed or a decentralized environment, the generals may get confused. So, for example, whenever this general is informing G1 is informing G4 to retreat, G4 can get a confused that whether or what he should do. So, that way in a decentralized or a distributed platform, achieving consensus over a message passing system can be difficult when you have this kind of malicious node, or you have nodes which starts working maliciously. So, we have a technical term for this kind of nodes, we call them as the Byzantine nodes, or we call this kind of failures as Byzantine failures. So, later on we will discuss about this kind of Byzantine failures in details, but in brief, that in the presence of this kind of Byzantine failures, the system can behave maliciously, or it may be difficult to achieve a consensus in a distributed environment. So, but as we know that if there is no failure in the system, then it may be easy and trivial to reach in a consensus. So, a generic algorithm can be something like this, like you broadcast the personal choice to all, and then you apply a choice function. Say in this case, if your choice is the maximum of all the received values, then you can achieve a consensus. So, here are 4 nodes, individual nodes make a choice of 10, 20, 30 or 40, and they inform their individual choices to all other nodes in the network, and whenever every node receives all the choices from all the neighbors, they can apply a max function to find out that what is the maximum. So, you can easily see that everyone will reach to the value 40 if they apply the maximum function of all the received values. So, whenever we are saying that achieving consensus in this particular architecture is easy and straightforward, it is under certain scenarios. So, these scenarios are, first of all, the system need to be faultless. There should not be any failure in the system, so that every individual node can receive the message correctly. And the second requirement is that the system should behave in a synchronous way. So, what is mean by synchronous way? We will look into the formal definition of a synchronous message passing system, but by definition a synchronous message passing system is something where it is expected that you will receive all the messages within some predefined time interval. So, here in this particular architecture, every individual node is expected to receive all the messages from the peers in a non-failure environment within a predefined timeout, and every node can wait for that much of time, and in a synchronous system it is expected that everyone will receive the message. So, once they receive the message, they can find out the maximum of all the received values from different messages and take that as a value for the consensus. However, achieving consensus can be non-trivial in case of a distributed environment due to the presence of multiple type of failures. Now, typically in a distributed system, we consider three different type of failures. The first one is called as the crash fault. So, a crash fault is something like a node suddenly crashes. So, the node suddenly crashes or the nodes become unavailable in the middle of a communication. So, you are not expected to receive any message from that particular node. So, this is one type of typical fault that can be a kind of hardware fault or a software fault, due to which the node or the process which is communicating with another one, that particular process fails. The second type of fault is network fault or the partition fault. A network fault is something when a network link fails. So, a network failure may result in a partition in the network. So, we can see an example of that. So, say assume that there are multiple nodes in the network and these nodes are interconnected to each other. So, we have multiple nodes in the network and these individual nodes are interconnected. Now, so we have few other nodes, they are interconnected with each other. Now, in this particular node, if this node fails, then if this link fails, then the entire network get partitioned into two different parts. So, we have one partition here and we have a second partition here. So, the entire network get partitioned and you are not expected to receive any message from any node of this partition to any node of this partition or the vice versa. So, this message communication will not happen because you had a bottleneck link and that particular bottleneck link has failed. So, under this kind of network failure, because this kind of partition can happen in the network, we say that it is a type of partition fault. We use the term partition fault to denote this kind of network failure. So, this kind of network failure can hamper reaching in the consensus. So, if a network failure makes a partition of the network, the nodes in one partition they becomes unavailable to the nodes in another partition. So, all the nodes cannot communicate with each other and come to a general consensus. So, these are the two typical type of faults which are coming from either the hardware failure or a software failure, but the third type of faults, that is the Byzantine faults, it is a kind of more difficult fault to handle in a distributed environment. So, a Byzantine fault is just like the example that I have shown you earlier. Here the nodes start behaving maliciously. Now, whenever a node starts behaving maliciously, you do not know that what would be the action for that node. The node can send a positive vote, or sometimes the node can send a negative vote. In case of say the crash fault or in case of a network or a partition fault, it is still expected, or you can find out, or you can make an expectation that what is going to be the effect of a network fault or a crash fault. But the effect of a Byzantine fault is difficult to guess, because it completely depends on how maliciously the node is behaving and what the node is doing. So, sometimes the node can give a vote against the consensus, or sometimes the node can give a vote in favor of the consensus. So, that is why handling Byzantine nodes become difficult in a typical distributed system. But while we are dealing with different kind of consensus protocols, we have to deal with these three different types of faults. Now, whenever we are talking about the distributed consensus protocols, we need to satisfy certain properties of the protocols. So, the first property is called termination. So, the termination property says that every correct individual decides on some value at the end of the consensus protocol. So, that means whoever be the correct or non-faulty node in the network, the non-faulty node must terminate the protocol and decide on one value, and that value should be correct value. Then the second property is the validity. The validity property says that if all the individual propose the same value, then all correct individual decide on that value. So that is the basic idea of this validity property, which says that if all the individuals in the node they propose on the same value, like the example that we have shown earlier, that if all the individual propose a value 10, then every correct node should come to a consensus with value 10. They should not deviate from that particular value. So, that is the validity property of consensus protocol. The third property is integrity. So, the integrity property says that every correct individuals decides at most one value, and the decided value must be proposed by some individual. So, the integrity property ensures that the consensus value should not deviate from the values which are proposed by individuals in the network. So, you should not get a value of 20 in the consensus if none of the nodes in the network proposes a value of 20. So, this is the integrity or the third property of a consensus protocol. The fourth property of the consensus protocol is agreement. The agreement property says that every correct individual must agree on the same value. So, that means, and that is the most important property of a consensus protocol, that all the individuals in the network they must agree on the same value. So, whenever they agree on the same value after termination, we call that the system has reached to the consensus. Well, so while dealing with consensus, we consider two different type of message passing system. One type of message passing system we call as the synchronous message passing system, and the second one is asynchronous message passing system. So, in case of a synchronous message passing system, so the message must be received within a predefined time interval. So, we have a kind of strong guarantee on the message passing delay, and you know a priori that what can be the maximum delay of message passing for this particular network. Now, this kind of synchronicity give you a simplification in designing the protocol, in the sense that you can think of that you will wait for certain duration, that duration will be the maximum lifetime or maximum bound on the message delay, and if you wait for that amount of duration, it is guaranteed that you will receive all the messages within that time. So, this is the synchronous message passing system, but in case of asynchronous message passing system, on contrary, we do not have any upper bound on the message transmission delay or the message reception time. So, we do not have any such constraint. Message can be arbitrarily delayed or the message delivery time can be arbitrarily long. So, in case of a asynchronous message passing system, you cannot expect that if you wait for a finite duration, you will receive all the messages with some certain probability or with some guaranteed probability. Now, designing a distributed system in a synchronous environment is much easier, because you have that particular strong assumption on the message passing delay, and that is why if you wait for that amount of duration, it is expected that you will receive all the messages. But in case of a asynchronous message passing system, because you do not have that much of delay, you have to also deal with the kind of fault that may come due to the asynchronicity nature of the system. That means, it may happen that you are waiting for certain duration and you may not receive any vote for some of the neighbors, because the message which is coming from those nodes in the network, they have observed some kind of unbounded or some type of very long delay. So, if you wait for certain amount, you may not receive the messages from all the neighbors. So, having consensus under this kind of environment is much difficult compared to designing a consensus protocol for a synchronous distributed system. Now, there is an interesting result. We call this result as FLP 85, or sometimes people call it as an impossibility result. So, the impossibility result states that in a purely asynchronous distributed system, the consensus problem is impossible with a deterministic solution if there is even a single crash failure in the system. So, in case of a purely distributed environment or purely asynchronous distributed environment, if there is a single fault in the system, you cannot design any kind of consensus protocol, or better to say any kind of deterministic consensus protocol for that particular system. But in this particular impossibility theorem, note the term deterministic consensus protocol. It is true that we will not be able to design any kind of deterministic consensus protocol, or we cannot have any kind of deterministic solution, but we can always design some kind of randomized solution or some kind of probabilistic solution for a purely asynchronous distributed system in the presence of failures. But this particular environment gives on a bound on what type of consensus protocol you can design for a distributed environment, and this is the foundational paper, foundational work for distributed system, which was initially proposed by Fisher, Lynch and Patterson in 1985, and in one of the top ACM conference on distributed system, ACM POTC 2001, this paper got the most influential paper award. So, I suggest all of you to look into the formal proof for the impossibility result. We are not going to that details. If you are interested, you can look into this paper and look into the formal proof that why it is impossible to achieve a consensus in a purely asynchronous distributed system in the presence of failure, but ideally this gives us a idea about for what type of system you can design a consensus protocol. Well, now whenever we talk about the synchronous consensus, there exist various type of consensus algorithms that people have designed in a traditional distributed system environment, like the Paxos, Raft, Byzantine fault tolerance or BFT type of consensus algorithms. People have tried to implement many of this type of consensus algorithm for asynchronous system as well by applying probabilistic nature inside it. So, we look into all those different type of consensus algorithm later, but ideally this gives us an algorithm that what type of consensus you can design for a distributed algorithm. Now, the correctness of a distributed consensus algorithm, that can be characterized by these two properties, safety and liveness. So, the safety property says that the correct individual must not agree on an incorrect value. So, that means nothing bad has happened in the system. So, the safety property ensures that you will never converge to an incorrect value, or the correct individuals in the network, they will never converge to an incorrect value. And the liveliness property, or in some book or reference manual they write it as liveness property. So, the liveness property states that every correct value must be accepted eventually. So, that means something good will eventually happen. So, if you are proposing some good values, so that good value will be committed eventually. Although there can be some time lag or there can be some delay in reaching into the consensus, but after the consensus protocol terminates, you will expect it to get a consensus value out of that. So, these are the two correctness properties for our distributed consensus that we need to ensure whenever we design a distributed consensus algorithm. Now, let us look into the consensus protocols from the perspective of a blockchain environment. So, the type of blockchain environment like the Bitcoin that we have discussed till now, they are kind of open environment in the sense like any node can join the network anytime. But the type of distributed systems that we are considering till now, like a synchronous system, synchronous distributed system, and the type of consensus algorithms that have been explored for a distributed system, the traditional distributed system, those kind of consensus algorithm relies on a message passing environment. So, a message passing environment means that every individual transfers some kind of messages to others, and then for waiting for some finite amount of time, they receives all the information from the peers, and after receiving all the information from the peers, whatever information they have received till now, they process those information, and based on that information they reach to a or they design a consensus parameter to come into the consensus. But because this kind of traditional distributed consensus algorithm like Raft, Paxos or Byzantine fault tolerant algorithm, they rely on this kind of message passing environment, they are designed particularly for a closed environment. So, in a message passing environment, you need to know that which node you want to transmit a message. Now, the moment you have this constraint, like the moment you need to know that which node you want to send a message, you need to know the identity of all those nodes. So, that way this kind of distributed message passing algorithms for having a consensus was mostly designed for a closed environment. But for blockchain type of environment, in Bitcoin applications, we are mostly talking about an open environment, or earlier we have used the term as a permissionless environment, where any node can join in the network anytime. Now, under this kind of environment, having a consensus protocol based on the message passing argument is difficult, because you do not know that who are the nodes in your periphery to whom you want to send a message. Now, in case of a consensus in an open system, we have two broad type of algorithms. The shared memory is one architecture that people have explored, but shared memory architecture, it is not suitable for internet grade computing, because you need to put a memory which should be readable and writable by every individual nodes in the network. In general, the shared memory algorithms we apply whenever we try to reach consensus among multiple distributed processes inside a system, but we apply the message passing in the other case. But as we have looked into that, message passing is not feasible in an open environment, because in an open environment like Bitcoin, anyone can join the Bitcoin network anytime, and under this kind of open environment, the challenge is that how will you ensure consensus under this particular scenario. So, let us look into that, how do we ensure consensus, and even before going to that, let us look into that why do we require consensus in a Bitcoin network whenever we are utilizing blockchain as the backbone of a Bitcoin network. So, as you have looked into that, Bitcoin is a peer-to-peer network, and in this peer-to-peer network, say let us take an example that Alice broadcast her transaction. Say Alice made a transaction to Bob, and she broadcast this transaction in this peer-to-peer network. Now, remember that this kind of broadcast is different from a traditional message passing system. For a traditional message passing system, you need to know that which are the peer nodes to whom you need to send a message, but this kind of broadcasting, it works like a flooding. It works like a flooding in the sense like you send the message to the subset of the people whom you know, then those nodes will further send the message to another subset of the people. Those people will again send it to another subset of the people. This way, by flooding the message in the network, the message will get propagated. So, that way it is different, the architecture of this flooding environment is different from a traditional message passing environment, where you need to know that who are the neighbors to whom you need to send a message. Now, flooding is more costlier compared to a normal message passing environment. So, that is why we restrict the flooding to certain applications. Now, in case of a Bitcoin peer-to-peer network, whenever Alice is proposing a transaction, Alice broadcasts the transaction in the peer-to-peer network. Now, here we require the consensus, because all the nodes in this network need to agree on the correctness of these transactions. How will you ensure that the transaction is actually coming from Alice and not from an attacker? The attacker may also impersonate Alice and can send an transaction in the network in the name of Alice. So, the network need to find out, come to a consensus that this particular transaction is coming from Alice and not from an attacker. So, as I have mentioned that in this particular peer-to-peer network architecture, a node does not know all the peers in the network, because this is an open environment. So, under that open environment, some nodes can also initiate malicious transactions, and you need to prevent the system from having this kind of malicious transactions. Now, in case of Bitcoin network, every node has a block of transactions that has already reached into the consensus. So, that are the blocks of committed transactions, which is stored in the form of a blockchain. And every node also has a list of outstanding transactions that need to be validated against the existing transactions in the block, that means the existing blockchain. So, that is an example. So, you already have a block of transactions. So, these are the individual block of transactions, block 23, 22, 23, 24. Inside every block, the architecture we have looked earlier. So, you have a Merkle root, under that all the transactions are organized in a Merkle tree. Now, every node has this blockchain and they have a set of new transactions. So, these are set of new transactions. Now, these new transactions need to be committed to the block and need to be added in the blockchain. So, to commit these existing transactions, the network need to validate that these transactions are coming from the authenticated person and not from an attacker. And for this we require the consensus protocol in a Bitcoin network. So, whenever we talk about the consensus in a Bitcoin network, so this is an interesting fact that why we are applying something called a blockchain. So, you can always have a per transaction consensus. So, you take every individual transaction and then validate that transactions. But if you do for per transaction consensus, it is inefficient because you have to run the transaction algorithm for every individual transaction. So, what we do, rather than running the consensus algorithm for every individual transaction, you run the algorithm on a block of transactions. So, that way you can make the consensus algorithm much efficient. So, you do not need to run the consensus for every individual transaction, rather you run it for a block of transactions. So, here comes the concept of blockchain, that we are representing the transactions in the form of blocks, and we are not representing it in the form of a transactions chain, rather we are representing it in the form of a blockchain for an efficient implementation of consensus. So, that is the objective of Bitcoin consensus algorithm. So, earlier we have looked into the concept of miners who actually participate in the consensus algorithm. Now, here we have three individuals or 3 miners, M1, M2 and M3. So, everyone has one blockchain in hand. Now, everyone has constructed or observed these transactions from the clients. Now, they construct a new block of transactions. So, M1 has constructed a new block of transactions from the transactions that he or she have heard of. M2 has constructed another block of transactions, M3 has constructed a third block of transactions, and interestingly it is not necessary that every miner will have the same set of transactions. There can be always the difference between the set of transactions that would be heard by the individual miners, and that is why the proposed blocks are different for different miners. So, the Bitcoin consensus algorithm, the objective is that among these 3 blocks, which block I will add to this existing blockchain. So, this is the problem of Bitcoin consensus algorithm. So, with this we will stop today. In the next class, we will look into that how the Bitcoin proof of work algorithm actually achieves the consensus under an open environment. So, see you all during the next class, and thank you.